Is my screen visible?
Yes, sir.
Yes, somebody please respond.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, so we will continue now. So in the previous class, we have seen the derivation of the elemental stiffness matrix for a beam element. Okay, so today we'll take a numerical based on this, right? So before taking the numerical, let us quickly see how the load vectors are calculated in case of beams. Okay, so let me start. So generally what we write your load vector, that is F. Okay, it is consist of three parts, that is the force at the point. Okay, then we have the force on the surface and the force on the volume. Okay, so force on the point is basically a point load. Okay, so it can be directly added in the global force matrix. Fs and Fe, Fs and Fe more or less same, because Fe can be converted into a surface load in form of a UDL. Okay, so let us quickly see how the force over the surface is calculated. So this is, let us say, Fs, and if you remember, it is generally calculated by integration over the surface, and we have n transpose. Okay, so this is the transpose of the shape functions into the force. Okay, so the force value generally it's a UDL value. Okay, and it is integrated over ds, that is integrated over the surface. Okay, so if you consider a simple beam, so let me draw a simple beam over here. Okay, so my beam is, sorry, let me undo this. Okay, so I have beam which is like this, right? And I have, let us say, this is my node number 1 and this is my node number 2. Okay, and the length of the beam is, let us say, L, right? Now over this beam, okay, generally what we do is we assume this side is your x-axis. Okay, and here on the downward direction we generally assume this is the direction in which the deformation is going to occur. So this is the positive direction, I can say, right? So now what I'm going to assume over here is the UDL. So this is the surface value, okay, or the surface load which is acting on this particular beam. Okay, let us call this value is, let us say, Q. Okay, generally we denote it by W, but W is already W symbol is already used for the direction or the deformation in the transverse direction. Okay, so right now you need to understand that the direction of the load is in line or in the direction of the displacement. Okay, so now in the previous class we have seen the values of n1, n2, n3 and n4. So this Fs, that is the surface force, now can be integrated. Okay, so here we have since it is a n transpose, so n transpose will look like this. So this is n1, this will be n2, this will be n3, and this will be n4. Okay, multiplied by t. So t is the force. So right now I have a force value as q. Okay, and ds is nothing but the integration of over the surface, a small portion of the surface. So generally what we do is we write this as 1 into dx. Okay, so if you are writing dx over here, so this will be integrated over the length now. Okay, so this will be from 0 to L. So let us focus on the first part. Okay, so this will be having 4 different components. Okay, n1, n2, n3, n4. So for the time being, let us focus on the first part. So this is let us say here. Okay, so I'm going to call this as fs1. Okay, so fs1 can be written as 0 to L. Okay, and this will be n1 into q into dx. Okay, so if you remember the value of n1, yesterday's class we have calculated something like 1 minus 3 times x square divided by L square, plus we have 2 times x to the power 3 divided by L to the power 3. Okay, into q into dx. Okay, So now, can somebody tell me what is the integration of this? Okay, please do the integration part and let me know the fs1 value, please. Yes. Yes, somebody please respond. What is the fs1 value? अरे
So
बोलो भाई.
LQ by 2.
Sorry.
LQ by 2.
LQ by
2.
positive or negative?
Sir,
Negative.
positive.
Negative or positive?
नेगेटिव सर.
पक्का नेगेटिव है.
Sir,
Yes sir.
positive.
हाँ, minus this is L by 2 into Q. Is it so? Okay. So this is fs1, right? Now similarly, you can calculate fs2 also. Okay, fs, let us say second component. Okay, so this is the second component, right? This one. So this will be nothing but the fs2 will be something like integration from 0 to L of n2 into q into dx. Similarly, you have fs, you have fs3 equals to integration of n3 into q into ds, and similarly you have fs4 as integration from 0 to L, we have n4 into q into dx. Okay, so now can someone tell me the values please of integration? N1, N2, N3, N4 already we have derived in the previous class. Okay, just for sake of your understanding, let me write down the n2 value. I think the n2 value was something like 4 divided by L minus 6 upon L square into x. This will be q into dx.
सर ये n2 की वैल्यू नहीं है ना सर, ये उसको डबल डेरिवेशन करने के बाद वैल्यू आई है.
N1 का डबल डेरिवेशन वाली वैल्यू है ये.
Oh, sorry, sorry. Sorry, I got disconnected. Let me share the window one more time. Okay. Right. Uh, yeah. Anybody? Tell me the value of fs2.
1 by 12.
Just a moment. Fs2 is
1 by 12 L square into Q.
1 by 12 L square into Q. Okay. Positive, negative?
Positive.
Positive. Okay. And how about fs3 and fs4? Yes, anybody fs3? करो जल्दी जल्दी करो, हमको न्यूमेरिकल भी सॉल्व करना है.
Sir, 1 by 2 QL.
Positive?
Yes, sir.
Okay, so it is something like L by 2 into Q. Okay, and fs4?
Minus 1 by 2 QL square.
1 by 2 नहीं होगा, 1 by
1 by
12 होगा.
12. 1 by 12. Yes, sir.
Okay, so these are the values. So at the end, what is going to happen is this, that is your fs. Okay, that is the surface force. Now we'll be having a 4 component, right? So the first component will be something like this is ql by 2. Okay, and this value will be negative. Okay, because just now we have seen this value is negative over here. Okay, I think fs3 का साइन बताओ तो कोई तो भी. fs3 should also be negative. Yes, somebody please tell me. fs3, is it correct?
Yes, sir.
Is it positive? It should not be positive, it should be negative. Please check fs3 value. Please check. Yes, please check this value.
पॉजिटिव ही है.
पॉजिटिव कैसे आ रहा है बेटा? अगर ये नेगेटिव है तो ये अगर नेगेटिव है, सो दिस शुड आल्सो बी नेगेटिव. बोथ वैल्यू शुड बी सेम.
सर fs1 शुड बी पॉजिटिव और नेगेटिव.
तुम लोग बताओ, डेरिवेशन तुम लोग कर रहे हो, बोथ वैल्यू शुड बी सेम.
fs1 is positive, like
fs1 is positive.
positive.
Okay, तो भैया ऐसे बताओ.
fs1 is positive.
fs1 is positive ना, ठीक है, then it's okay. Both values should be same. Okay, that is the deal. Okay, so now you see this is the final load vector. Okay, now we just try and understand this, what is happening over here. Now if you remember, when we have gone for the derivation of the stiffness matrix, so here we have written w1 theta 1 and this is w2 and this will be theta 2. So this particular two components, they are related to the displacement, and these two components, they are related to the rotation. Now this displacement always results in reaction. Okay, and rotation always results in what? Moment. Okay, so basically what I'm trying to say over here is this is very much similar to your matrix method. So if you have a load which is like this, okay, and its value is, let us say, w. Okay, and the length of the beam is, let us say, L. Okay, so in that case, the whatever load is there, so W into L will be the total load, and this total load will be acting in form of a on the beam, and if you take a reaction of this this particular beam, so if you calculate the reaction, it will come like this, isn't it? So the total load is basically divided, and half of the load will be transferred on both the ends of the beam. So this is nothing but QL divided by 2. This is nothing but QL divided by 2. And if this is a fixed end beam, then you will always get a reaction which is something like this. So this will be WL square by 12, isn't it? And here also you will get WL square by 12. I think I have written over here by mistake Q. This should be W, isn't it? So the same thing you are getting over here. Okay, so remember in your matrix method also, what you are doing, you are calculating the fixed end moments and reaction, and that you are giving as a external loading in a global load vector. Am I right? Is it okay?
Yes, sir.
Okay, so the same thing has to be repeated over here. So if it is a UDL, you are going to get these values. If it is a trapezoidal load or triangular load or any other load, so whatever fixed end moments are there, that you have to consider as a loading part. Okay, so this is a simple derivation for the calculation of the uh, external load vector in case of beam problem. So now let us quickly take a simple numerical. I'm taking a solved problem from the book so that you can have results comparison whether you are doing everything correct or not, so that you can check. Okay, so let me draw a problem for you. So this is a simple beam. Okay, let me just slightly go down. So this, oh, sorry, so this is a simple beam. Okay, and we have a fixed end at one on the left hand side, so this end is fixed. Okay, and we have a roller support over here, and we have a roller support over here. Okay, so these two roller supports are there, and on this beam we have a UDL. Okay, so let me draw a uniformly distributed load over here, and its value is given to you, that is 2 kilonewtons per meter. And there is a concentrated load also which is given, and this concentrated load is acting at the center, and its value is given to you as 10 kilonewtons. Okay, the distances are also given. So this total distance here, this distance is given to you as 6 meters. Okay, and this total distance from this end to the other end, so this distance is given to you as 4 meters. At the same time, this distance, that is the distance between this load and this end, is given to you as, let us say, 2 meters. Okay, so this is this information is given over here, and the basic information is given, that is EI is assumed to be constant. Okay, so the value of EI is not at all changing irrespective of the left span or the right span. Okay, so the analysis procedure is very much similar to the matrix method process. Okay, but since we are using the finite element method approach, so we have to use step by step process. So let us go for the solution of this particular problem. So now in the first step we have to go for the discretization, right? So what I'm going to do is I'm going to discretize this particular beam with the help of two elements. So this will be the first element, and this will be your second element. Okay, so what I'm going to do is I'll call this as node number 1, this will be node number 2, and for the second element this will be node number 2, and this will be node number 3. Okay, and I'm going to call this as element number 1. Okay, and I'm going to call this as element number 2. Okay, so we have to generate the stiffness matrix in the next step. So we have already gone for the derivation of the stiffness matrix. Okay, so I'm just directly going for the stiffness matrix. Okay, so can you generate the stiffness matrix please for first element? Yes, please generate the stiffness matrix for the first element. So this is the generalized expression for calculating the elemental stiffness matrix. Okay, so this we have already derived in the previous class. Okay, so you can make use of this. Okay. Can someone tell me what is the elemental stiffness matrix for 1?
So 0.055.
EI by 18.
First element, one element is how much?
EI by 18.
Sorry.
EI by 18.
So is it, are you taking outside, or shall I write it inside only?
1 by 18. If EI is taken a common.
So 0.055.
So what I'll do, I'll take EI outside. Okay, is it okay?
Yes, sir.
Yes, sir.
So this is E and I. Okay, and how about this one? The first element will be
1 by 18.
1 by 18.
Same value is coming 0.055.
Yeah, okay, I'll put it 1 by 18. Okay, that will be better. Okay,
Yes, sir.
and what about this second one?
1 by 6.
1 by
6.
6. Okay, so I'm guessing this is also 1 by 6, right?
Yes, sir.
How about this one?
2 by, that is 1 by 18.
1 by
18.
18. So this is also 1 by 18. And the last one?
1 by 6.
1 by 6. Okay, how about this
1
one?
by 18 should be the negative, that second value.
This value.
Yes, sir.
Okay. What about others? ये वाले बताओ.
Sir, 2 by 3.
2 by 3. Okay.
Yes.
How about this?
Minus 1 by 6.
Minus 1 by 6. Okay. How about this?
1 by 3.
Positive, negative.
Positive.
Okay. And how about this one?
Positive 1 by 18.
Okay. And how about this one?
Minus 1 by 6.
Minus 1 by 6. Okay. So this will be also minus 1 by 6. Okay. And the last one?
2 by 3.
Sorry?
2 by 3.
Positive.
Yes, sir.
Right. So you see, we have successfully calculated the elements of the stiffness matrix over here. Okay, so this will be your K1. Okay, now as far as the first element is concerned, we have UDL also on the first element. Okay, so remember, on this element we have a UDL. Okay, so here we have a UDL, and its value, I think it is given in the numerical. This is 2 kilonewton per meter. Okay, so now for this first element, now you will have to generate the force vector also, right? So this is the force vector, that is Fs. This is for the first element. So just now we have seen the equations. Okay, so here we have seen this is QL by 2, QL square by 12, and so on. So please do the calculation and please let me know the values, please. Yes, please tell me the values. It is simply QL by 2, that is 6. बराबर है? Yes, students, is it okay? 6 over here and 6 over here. बराबर है?
Yes, sir.
Okay. बीच वाली बताओ. बीच वाली बताओ. This is QL square by 12. How much is that?
Sir, 6.
This is positive, right?
Yes,
So
sir.
this will be 6. Sorry, this will be 6 and this will be minus 6, right?
Number 6. Yes, sir.
Okay. So now you can use the same expression which is given over here, and then you please calculate the value of K2 as well as FS2. Okay. So your K2 will come something like this. I'm taking out EI outside. Okay. Done?
Yes, sir.
Yes. Can someone tell me the values, please? K2.
Sir,
What
3
should I
by
write over here?
16.
Sorry?
3 by 16.
3 by 16. Okay. And how about next one?
3 by 8.
3 by 8. Okay. Next one.
Minus 3 by 16.
Okay. Next one.
3 by 8.
3 by 8. Okay. So this will be 3 by 8 one more time. What about this 2,
1.
1? Very good. Next one.
Minus 3 by 8.
Minus 3 by 8. Okay.
And next value 1 by 2.
1 by
2.
2. Okay. I think this is minus 3 by
3 by
16.
16.
Okay. And this is minus
Minus
3 by 8. Okay. And how about this one?
3 by 16.
3 by 16. Okay. And how about this one?
Minus 3 by 8.
Minus 3 by
8.
8. Okay. And lastly, I think it is 3 by 8. Okay.
Yes, sir.
Then I think we have
1
this
by 2.
1 by 2. Okay. Then we have minus 3 by 8. And how about last one?
1.
Sorry?
1.
1. Okay. While calculating FS2, okay, so what we have understood is we have to consider this beam as a fixed end beam, and the external load is applied over there, and accordingly whatever reactions are there, that we have to consider as a external force. So for this particular beam we have a concentrated load which is acting at the center, and its magnitude, I think it is 10 kilonewton. Okay. So accordingly you can get the fixed end moments. Okay. So this you have already done plenty of times in the matrix method. So
5.
what is this? Kitna aa raha hai?
5.
This is 5. Next one.
5.
Next one.
5.
This is I think minus 5, right?
Yes, sir.
Okay. So basically your this part is now completed. So now what we have to do is we have to go for the assembly. Okay. Assembly also you have already done this a couple of times. So basically this is your K1. Okay. So K1 is having the first element. Okay. And first element is having a nodes, something like this will be a contribution of the first node, and this will be the contribution of the second node. Okay, here also this will be contribution of the first node, and here there will be contribution of the second node. Okay, but if you want to have a specific thing, so basically this is your w1, this is your theta1, this will be your w2, this will be your theta2. Similarly, this will be w1 theta1, this will be w2 and theta2. But in case of the second element, this will be your w2, this will be your theta2, so this will be also w2 and this will be theta2, and this remaining column, this will be w3 theta 3, this is w3 and theta 3. Okay, so now accordingly, now you have to go for the assembly. Okay, so please do the assembly and let me know the global stiffness matrix. So I'm going to write down over here K global. Okay, so let us take EI outside and let us try to have the global stiffness matrix. Okay, so your global stiffness matrix will be of size 6. Okay, please assemble the matrix and let me know the values. You can also calculate the global force vector, okay, by assembling the fs1 and fs2. Yes, students, please tell me the values. Have I written correctly? एक बीच वाला वैल्यू बताओ. 2 2, that is assembly part.
So 35 by 144.
Which one here?
Yes, sir.
Okay, 35 by 144. How about next one?
5 by 24.
5 by 24. Okay, this will be also 5 by 24, I suppose.
Yes,
And
sir.
what about this one?
5 by 3.
Sorry,
5 by 3.
5 by 3.
Yes, sir.
Okay.
So please ask someone to cross verify.
Sorry.
Sir, ask someone to cross verify.
Yeah, I'm asking the same thing. Okay, please somebody verify. Are they correct? Yes, someone please verify. अरे करेक्ट है नहीं है, बताओ, कोई तो बताओ.
Yes, sir.
Okay, great. Fine. How about your global force vector? It will be also assembled. So this is 666 and this will be -6. So this is 666 and this will be -6. And here you will have something like +5. Okay, here you have +5, here you have 5, and here you have -5. Okay, so as a result of this, I think you should get here 11 and here you should get -1. Am I right? बराबर है ये?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Right. So this is our global force vector. So now what we have to do is we have to apply the boundary conditions, right? So every node has got two degree of freedom. So one is the deformation in the vertical axis and second one is the rotation, right? So as far as this problem is concerned, node 1 is basically fixed. So since it is fixed, so it is not allowed to move or it is not allowed to rotate. So as a result of this, what now you will have to do is you have to just simply remove the first row. Okay, okay, this is for the deformation and this is for the rotation. So this will be completely now gone. At the same time, you have to remove the respective columns as well. Okay, so let me write down the unknown vectors over here. So here you will have W1, this will be theta1, this will be W2, this will be theta2. Okay, this will be W3 and this will be theta3. Okay, so after applying the boundary conditions, we are ending up with 4 by 4 matrix. Still we have two more boundary conditions, like node number 2 is not allowed to move in the vertical direction, and at the same time node number 3 is not allowed to move in the vertical direction. However, the rotations are allowed. So basically now in this particular case, the deformation has to be removed. So your W2 term, it should be removed because it is not allowed. Okay, so your W3 is gone. Accordingly, the third row of the stiffness matrix will also be gone. Sorry, W2, not W3. At the same time, your W3 is also gone because it is not allowed in the allowed to move in the vertical direction, and accordingly, your this column, this will be also now gone. Okay, so as a result of this, what you are going to end up with something like this. So your global stiffness equation, okay, so your stiffness equation, generally it is K into delta equals to F. So now your K will become something like EI. Okay, now you have only two terms. So here you have 5 by 3, here you have 1 by 2, here you have 1 by 2, and here you have only 1, and the delta term will be simply theta 2 and theta 3. Okay, and this will be equal to -1 and -5. Okay, so now you have to solve this. Okay, and after solving you will get the value of theta 2 and also you will get the value of theta 3. Okay, so please tell me the values. Solve this. So you have to solve this in terms of EI.
Yes, sir.
Yes, anyone? Theta 2 and theta 3.
Sir, 18 by 17 EI.
Just a moment. Let me write down first. What is theta 2?
18 by 17 EI.
EI डिनोमिनेटर में है कि न्यूमरेटर में?
Sir, denominator.
Okay, so this is 18 by 17 EI. Okay, is it negative or positive?
Sir, positive.
Positive.
Theta
Okay.
3 is minus 94 by 17 EI.
Minus 94 by
17.
EI. Okay, somebody please cross check this.
Yes, sir.
Yes, sir.
Same you are getting?
Yes, sir.
Okay, great. I am also getting the similar kind of answers in the books. Okay, so I'm guessing this is correct, right? So now our problem is solved. So rest of the thing is pretty simple. What we have to do is if you want to do the calculations of reaction, so you just have to substitute these values, that is W1 will be 0, theta 1 will be 0, W2 will be 0, theta 2 whatever value is there that you can put, W3 is 0, and theta 3 whatever value you have obtained that you can put, and you just multiply this accordingly. You are going to get the reactions. Okay, so here if you multiply the first row with this column, so whatever value you will be getting, that will be nothing but the vertical reaction. If you multiply the second row with this particular column, that is the unknown deformation, you are going to get the moment at the node number 1. If you multiply this third row with this column, what you are going to get is the vertical reaction at joint number 2, that is the roller support. And if you multiply this fifth row with this unknown deformation, you are going to get the reactions at the roller support, which is there at the end. Okay, then depending on the requirement, like if you want to have the bending moment and shear force diagram, I hope you can do this. You have already plotted shear force and bending moment diagram in the matrix method, so the same process has to be adopted over here. But here I would like to tell you something different, which probably you might not have studied in the matrix method. Okay, so please pay attention over here. So for example, like I want to know what is the value of deformation, or what is the value of U, or what is the value of W at the center. Okay, so at this level, what will be the value of deformation? So here I am just talking about the element number 1 only. Okay, so let me draw the element number 1. Okay, so here is my element number 1. So in element number 1, this is node number 1 and this is node number 2, and the length of this particular member is, I think, 6 meters. Okay, let me please check. Yeah, it is 6 meters only. Okay, so now if I want to know what is the deformation at the center point, okay, so somewhere over here, let us say I have a p value. Okay, so how to get this deformation at this particular point? So for this purpose, you know, there is a simple expression, that is W is of you can calculate something like N1, N2, N3 and N4. Okay, multiplied by, you have this is the deformation at the first point, W1 theta 1 W2 and theta 2. Okay, if you refer the coefficients of, let us say, n1 and say n2, n3 and n4. Okay, I'm just writing the value of n1 only. So if you write n1, so n1 comes out to be 1 upon 3 x square divided by L square. Okay, plus we have 2x to the power 3 divided by L to the power 3. Okay, so this is n1 expression. Similarly, you can get the value of n2, n3, n4. Okay, so right now, if you see this point P, so this point P is at a distance of, let us say, 3 meters, which is measured from the starting point, that is node number 1. So what I have to do over here is, in place of this x, I'm going to put 3 meters. Okay, and in place of this L, I'm going to put 6 meters. Okay, so if you do the calculations, okay, so can you just give me the values, please? What is the value of n1? कितना आ रहा है n1? Yes,
Sir, 0.5.
0.5.
Yes, sir.
Okay, so if this is 0.5, can you calculate the value of n2 also? N1, N2, N3 and N4. These are required values. Okay, without that we won't be able to get the deformation, right? Just give me the value of N2.
Sir, 3/4.
Sorry,
3/4.
positive, negative.
Positive.
Okay, are you sure it is 3/4? Someone please cross check. Yes, someone please cross check the value of N2.
Yes, sir. 3/4.
Okay. Similarly, I think you should get the value of N3 as 0.5.
Yes, sir.
Okay, and this should be minus 3/4. बराबर है?
Yes, sir.
Is it correct?
Yes, sir.
Fine. So if I want to calculate what is the W, that is the vertical deformation at point P, so I'm just writing WP equals to, the value of N1 is 0.5, N2 is 3/4, this is also 0.5, and this is minus 3/4. Okay, multiplied by, you have W1. So W1 is 0 because it is fixed end, theta 1 is also 0 because it is fixed end. Then W2 is also 0 because there is a roller support. But whereas if you see the theta 2 value, so theta 2 value is positive 18/7 EI. Okay, so this is something like 18/17 EI. Okay, so now if you multiply this, so this is going to give you the deformation at the center of the first beam. So can someone tell me the values, please? It should be there in terms of EI. (18/17 EI). into minus 3 by 4. That's it. So simple calculations.
Minus 27 by 34.
Minus 27 by 34 EI will be there in the denominator. Okay. So you just understand that this deformation which is there at the center, it is not in the direction in which we have assumed. It is exactly the opposite of this. Okay. Remember, when we have gone for the derivation, we have assumed the vertical direction W like this. So since this is negative, so this point is basically going up. Okay. So you will be getting a shape which is something like this. Okay. So in order to get this particular shape, what we have to do is we have to take n points or several points in between. Let us say if this is 6 meter span beam, so we can have 6 points at 1 meter each, and then we can find out what is the deformation at every 1 meter, so that now you can get the exact plot of the deformation. So most of the softwares like STAD is there or SAP is there. How we are getting the deform shape? It is getting the deform shape like this only. Okay. Otherwise, in matrix method, if you use the matrix method approach, what you will get? You will only get the shear force and bending moment diagram and the reactions. But if you use the finite element method approach, you will be able to get what is the deformation, what is the shear, what is the bending moment at a particular point, so that you can plot the exact value of the required result, maybe shear force, bending moment, or deformation at a particular point. Okay. So this is not possible in the matrix method. Okay. I hope this is understood to everybody. Are there any questions as far as this portion is concerned? This is almost a repetition of the matrix method, isn't it? Okay. So yes, Ketan, you want to say anything? Okay. So I think we should stop now. If you have any queries, we can discuss. Otherwise, you can leave the meet. Okay.